Peter Stone, who is the founder and director of the Learning Agents Research Group at the Department of Computer Science at the University of Texas at Austin, as well as the Associate Department Chair and Director of Texas Robotics. He's also an Executive Director of Sony AI America. For folks in the Marl community, it's literally impossible to get through your PhD without reading a ton of Peter's papers, whether it's through RoboCup, his recent work at Sony on building a superhuman racing agent, work on cooperative autonomous vehicles, or multi-agent learning algorithms. So we're super excited to have you, and take it away whenever.
All right, thanks a lot. Thanks for inviting me. Thanks all for being here, and it's a pleasure to talk to a group that's really focused on multi-agent learning, and it was very difficult for me to choose what to talk about. It's sort of foreshadowed by Eugene there. So what I'm going to do is I'm going to sort of give a taste of several different things. And hope to encourage you to learn some more details in from the papers and things. I'm going to try to highlight the main results. But first, I'll just give you a quick introduction to some exciting times that are going on at UT Austin. We have a new machine learning lab that was prompted by winning one of the first institutes for foundations of machine learning, one of the first NSF and AI institutes. That's headed by Adam Clivens. I'm the director of Texas Robotics, and we have a beautiful new space on campus. It used to be a gymnasium, obviously, but now full of robots. We have lots of different faculty across different departments. This is a slightly out-of-date slide now. We've had some new additions and a couple departures, but just to emphasize that we have people who publish at ICRA and IROS. These are the robotics folks, and still growing and still interviewing. One of the so just by way of introduction, for those of you who don't already know me, I like to give in almost all the talks the same one-slide introduction to my lab. We do a lot of different things in my lab, but they're all united by this question. And really, in some sense, everything I've done over the past now almost 3 decades of research in AI has been motivated by this question: to what degree can autonomous intelligent agents learn in the presence of teammates and/or adversaries in real-time dynamic domains? We therefore publish in a bunch of different sub-areas of AI and in many different conferences. I'm going to emphasize in this talk, I do some things in my lab that are machine learning but not multi-agent systems, some things that are multi-agent systems but not machine learning. I'm going to emphasize in this talk some of the things that are at the intersection of the two. I'm also going to try to span the sort of research that's more theoretical and algorithmic, which I sometimes call bottom-up research, and also more applications-driven research, which is sort of top-down. We do both in my lab. I've had theses and papers that sort of come from both directions. When I give a one-slide introduction, it's a lot easier to talk about some of the motivating application domains that have driven my research. One is RoboCup, where we try to create agents that can act independently, but with teammates and adversaries to play the game of soccer. I'll talk a little bit more about that in a minute, but right now this is what the standard platform league looks like. And I know the video is a little choppy. These work a little better in Zoom, I think, but these are some videos of when the robots were using the robots we're using are the SoftBank Now robots. They're no joysticking, no human involvement. Once they're playing, they're fully autonomous, sensing, deciding, and acting. So RoboCup has been a big inspiration domain for me. I also work a lot now on what I call the building-wide intelligence, or just sort of having robots be in the environment with us, sharing a space, becoming a part of the social fabric of the building. This video is the result of some joint research with Ray Mooney on grounded language learning for real robots, where the people were typing in dialogues to a robot, and the robot was asking them for clarification, and the initial requests and the robot's final understanding of what they wanted became sort of training pairs for grounded language learning. And at the end of sort of a week-long experiment, these dialogues became shorter. The robot got better at satisfying people's requests. But in general, this is all part of a research grand challenge of just having social robots in our building, being able to understand when people want to be entertained, when they want to be helped, when they want to be left alone, having multiple robots interact with one another. So that's been very inspiring. And another application domain that's always been inspiring to me is autonomous driving. I had a car back in the DARPA Urban Challenge back in 2007. And we now think a lot about autonomous intersection management and how can we improve traffic flow. And this is a video I like to show of a multi-agent system where there's each car is still controlling itself, but there's a sort of a reservation-based system such that the cars are calling ahead for a reservation in space-time that doesn't, and there's a single program at the intersection that's taking the place of a traffic signal that's either accepting or rejecting these reservations and ensuring that as long as cars follow those reservations, there'll be no collisions. So I could give a sort of a 1 hour talk on any of these sort of application domains. But I'm not going to do that. I am going to take just 2 slides to. I couldn't resist talking about RoboCup a little bit more because it so happens that tomorrow morning, less than 24 hours from now, I'm going to be getting on a plane to Bangkok for this year's RoboCup competition. It's our first in-person one in 3 years, and people from around the world will be coming. Many of them focused on robot soccer, where our grand challenge is to beat the World Cup champions on a real soccer field by the year 2050. And we still have a ways to go, but there's a lot of features of this challenge as a great challenge problem for multi-agent systems, for multi-agent learning. There's several different leagues. I like to show sort of what it looked like back in the first years, and I think 1997, 98, the robots were sort of moving slowly and in sort of very haphazard ways, running into walls, falling over. Whereas just a few years later, they were moving much more quickly and smoothly. We were starting to see teamwork, better individual play, better coordinated play, better adversarial play, and this has continued to improve over the years. And so if you come to RoboCup now, you can see really, really big progress. Also, it's important to emphasize that RoboCup is not just about robot soccer. There's other leagues. There's RoboCup Rescue, which is a disaster rescue scenario, RoboCup at Work, and then another one that my team participates in is RoboCup at Home, where we have robots that are trying to do tasks like taking out the trash, so that where the robot has to go and find the trash bins in an apartment and take out the bags and take them to the entrance, but also things like putting away groceries, helping interacting with people. There's a lot of human robot interaction aspects to this, to RoboCup at Home. So I guess the main thing I want to get across here is that these for people who are I think some students are very motivated by the algorithmic and theoretical bottom-up kind of challenges. For people who are more motivated by really challenging applications and using those to come up with the research insights, RoboCup is full of great challenges, and I encourage you to learn about it and participate in it if you haven't in the past. So I'm excited to see how the teams have been doing over the past few years. So that's a quick introduction. The title that I sent is sort of for this talk was topics in multi-agent reinforcement learning motivated by ad hoc teamwork. And again, I could have decided to just give a full talk on ad hoc teamwork. And there's actually a recording, now that because of the pandemic, that lots of talks have been recorded. So I try not to repeat talks too many times. There is a full keynote style talk on ad hoc teamwork that I gave at ICHCAI 2 years ago. So instead, for this, what I'm going to do is I'm just going to, for those of you who aren't familiar, give a little bit of the motivation of ad hoc teamwork, but then go on to some of the more sort of isolated problems that we've worked on. So the motivation for ad hoc teamwork is that, well, we all know what teamwork is. People do it, right? When they're, when they're on a search and rescue team, robot soccer, typically there's pre-coordination, both for these human teams and for these robot teams, where the people or the robots are given protocols or trained together to be sort of a well-oiled machine. And some of my early research as a PhD student was on coordination languages for teams, and the definition of a type of domain called periodic team synchronization domains, that soccer is sort of an example of, where you can have periodic times like before the game and halftime where there's full coordination bandwidth, but then you need to go and act much more dynamically when out in the real world. And we introduced the concept of sort of a locker room agreement to sort of pre-coordinate. And then also back, I guess, more than 20 years ago now, Rich Sutton and I showed that you can use distributed Sarsa Lambda for learning a keep away task. Here, the red agents are learn over the course of 24 hours or so to keep the ball away from the blue agents, and did so better than highly trained or reasonable hand-coded heuristics and other baseline policies. And that was all presented in ICML 2001. In contrast, ad hoc teams, the idea is that each player is an individual. They don't get to be programmed to work with their teammates. They're going to have unknown teammates that are going to be programmed by others. You may or may not be able to communicate with them. The teammates are likely to be suboptimal, and if they are, you can't change that. You have to deal with that. You have to adapt to that. And so, people are very good at this. I can go play a pickup soccer game with people I've never seen before. We'd like to get robots to be able to do the same thing. If there's a disaster and I bring a robot and many other people bring robots from around the world, we don't want to have to reprogram them to work as a team. We want them to figure out for themselves how they can be a good team player. What should they do in the context of the current team that they're a part of? And so a challenge that we introduced 10 years ago now or so was to create an autonomous agent. That's the ad hoc teamwork agent, or the ego agent, that's able to efficiently and robustly collaborate with previously unknown teammates on tasks to which they're all individually capable of contributing as team members. So, they're sort of the pickup soccer analogy is everyone's already a good soccer player, but they've never worked together as a team before. I see a hand up. So yeah, Polly.
Hi, Peter. Just a question to clarify. Point number one, these are definitely cooperative tasks. And number two, are there any adversaries? Because in a game of soccer, there are adversaries.
Yeah, so good points. In the sort of pure definition of ad hoc teamwork, we do assume that it's fully collaborative, so that there's no individual preferences, that there's a joint common utility function. Now you can, as you suggest, you can generalize that slightly and talk about more sort of coordination as opposed to full-on teamwork. And so I have a survey with Stefano Elbrecht, who I think is on your schedule for a couple of weeks from now, on agents modeling other agents, and that sort of generalizes this concept. The advantage you get by assuming that they're teammates is you don't have to protect against the worst case. You don't have to sort of do the minimax kind of reasoning, like the other agents are out to get me. They might be incompetent, right? Your teammates can be anywhere from experts to novices, but even if they're novices, they're not trying to thwart you. They're at worst sort of random, and so that's something you can leverage if you make that assumption. And then whether or not they're adversaries, that depends on the domain. So yeah, if you could be in the soccer context, yes, that's right. There's adversaries, but you can have ad hoc teamwork domains where it's there's no other agents in the domain. Good. Those are good clarifications. So, when you're doing ad hoc teamwork, you need, some of the things you need to do. You need to assess capabilities of the other agents, assess their knowledge states, do plan recognition, and estimate the effects of your own actions on your teammates. And so the key here is that you need to be prepared. An agent needs to be prepared to interact with many types of teammates. either more mobile, more or less mobile, better or worse at sensing, possibly able to communicate or not. And the observation here is that a good team player's best actions will differ depending on its teammates' characteristics. And so I think this is actually going to become a more and more important practical question or capability for autonomous agents as we get closer and closer to a lot of agents being out there in a long-term autonomy kind of setting. Where you have a robot that's on for hours or days. It's going to come across other robots that it hasn't been that aren't programmed by the same agents or the same people, and but there may be cooperative tasks that they need to do on the fly. So like I said, I think this is a fascinating topic, and it can motivate I think dozens of PhD theses. It's not at all a solved problem. I've had a few from my lab. There's other people working on it from around the world. And I again encourage to learn about ad hoc teamwork especially if you're looking for sort of new problems in multi-agent learning. But rather than talking just about ad hoc teamwork, I sort of have picked just a small set of topics that I think I hope will be of interest to this group, and they're designed to sort of span the gamut from a very theoretical piece of work that was done by a former PhD student of mine, Doran Chakraborty, many years ago now, but that I think is very elegant, and I think deserves to be sort of there's a lot of opportunity for it to be built upon. And so I'm going to do a little bit of a deep dive into this topic that'll come next. I'm then going to give some very brief sort of summaries of some work on reducing multi-agent learning for reducing traffic congestion that's motivated very directly from some of the work here by people here on this call at Berkeley, and also a recent CVBR paper on end-to-end driving with cooperative perception. And then I'll end with, however much time I have at the end, a little bit about our recent Nature paper at Sony AI on outracing champion Gran Turismo drivers with deep reinforcement learning. So it's a lot to cover in the time we have, and so this is what I'm opting to do. Like I said, is to sort of give the highlights, try to motivate why you should be interested in it. Of course, there's full details in the papers that you can find here, and I'm always happy to answer questions. So this work on convergence, targeted optimality, and safety in multi-agent learning is, like I say, coming from the very theoretical side of multi-agent learning, which was, I think, much more a focus of the community at that time, prior to the sort of the focus now on like what's the biggest applications can we do if we run relatively if we're using neural network function approximators and relatively standard algorithms without in many cases we don't really have a deep theoretical understanding. So this is sort of a throwback to the days when that was the focus. What can we prove? And from the game theoretic perspective, in this case, we were thinking of agents that are involved in a repeated matrix game, which are end player and action games, where on each time step, each agent just sees the joint action and then the payoff for every agent. And the question is there any way for an agent to ensure certain payoffs against unknown opponents? What is it? What is it that we can prove? And even this question in multi-agent learning of what are well-posed questions to try to prove can be difficult. I will point out that everything I talk about here I'm going to talk about it in the zero-sum adversarial perspective, but it can also be extended to apply to unknown teammates as well. And Doran's thesis does that. So this is really the one-slide summary of the algorithm, the properties of the algorithm that we introduced. It was called Seamless, Convergence with Model Learning and Safety. And it's the first multi-agent learning algorithm that has simultaneously has all three properties shown here, which are all desirable properties for a multi-agent learning algorithm. One is that if the agent that you're controlling happens to be playing with only copies of itself, so it's a self-play agent, they're all seamless agents, then they will converge to a Nash equilibrium of the game. If the agent that you're controlling is playing against a set of memory-bounded counterparts, or of say opponents, with a fixed memory, with a bounded memory size that we know, we'll call K-max, then it'll converge to playing the best response with a high probability to those agents. So we call this targeted optimality. It's going to be optimal for a targeted set of possible opponents. And the memory bounded agents are, we're going to say, I'll define exactly why it's important that they're memory bounded and what we're assuming about them. And then the third property is, if the agents you're playing against are neither copies of itself nor in this class of memory bounded agents, then it will converge to the safety, the minimax payoff, the safety policy, like the one that assumes that the other agents are out to get you. And so the high level view of how to, and so these are, it was actually very tricky to think about how could we do all of these things simultaneously. The high level view of this algorithm is that it starts out by trying to coordinate to a Nash equilibrium, assuming all the other agents are seamless agents. And if they are, then convergence will be achieved. If it can identify that the other agents are not following a Nash equilibrium, so that if it gets evidence that they're not seamless agents, then it will next try to model them as being memory bounded agents with this maximum memory, and it will again identify whether or not this statement is a true model of them, and if it does, then it's going to if it is, then it's going to converge to the optimal sort of exploitation policy. And then on the other branch, if it identifies that they don't have this property of being a memory bounded agent, then it'll fall back to its minimax optimal policy and play that forever. And so just as I know some of this is a little bit hard to grasp at that high level. So let me give this a concrete example. A common matrix game is Battle of the Sexes. With this, the motive, the cover story for this one, there's a cover story for Prisoner's Dilemma and Chicken. The cover story for Battle of the Sexes is that you have two agents, Bob and Alice, and there's they have to coordinate with, this is before the days of cell phones and texting, so they don't know, they know they want to meet tonight after their days of work at various different places. They both know they want to go to a concert together. But Alice or Bob prefers going to a concert where Bach is going to be played, and Alice prefers going to a concert where Stravinsky is going to be played. So Battle of the Sexes is sometimes called Bach-Stravinsky. They both prefer to meet up together than to go to different places. But they each have a preference for one over the other, and so you get this payoff matrix. And there's three Nash equilibria where they would both always choose Bach or always choose Stravinsky, or there's a mixed equilibrium as well. So the way Seamless would approach this now is, if it's playing against it's playing with an unknown agent, is it will first use a sort of a Nash equilibrium solver that will differentiate between these Nash equilibria and compute a schedule that they would each play. So assume the agents are choosing the mix. Say this Nash equilibrium solver gives preference to the mixed strategy Nash equilibrium, in which Alice picks Bach with probability 1/3, and Bob picks it with probability 2/3. Then they both sort of do random draws from this mixed strategy for some designated number of episodes, and how many episodes you have to choose to be able to make it converge in polynomial time. So these are chosen carefully, and with the details in the paper. But at the high level, they play their part of the Nash equilibrium. If the other agent deviates from the expected number of choices in those, and plays by some certain amount, then if they all are sort of within some bound of the expected number of plays for that Nash equilibrium, then it just stays in this loop. But if one of them does deviate, it looks like it's not actually playing its part of the Nash equilibrium, they fall into this sort of signaling mode, where they play according to some fixed behavior. This, again, there's some intricacy to exactly how this is chosen, but it's chosen in such a way that, the first time they play the first action, a single designated action, Kmax plus 1 times. The next time they get into this state, they would play A1 Kmax times followed by some other action, and then afterwards they do Kmax plus 1 times. The reason is this is going to help us distinguish whether the agent is a memory bounded agent or not. So if they're, if they would have to do the same thing, they wouldn't be able to sort of follow this schedule unless they have a memory that's longer than Kmax. And so we'll check for consistency, and then either go back to the Nash equilibrium solver or continue on. And so they'll be able to either converge to Nash equilibrium by just playing it. They'll be able to detect when they're not in the Nash equilibrium, and in that case, they're going to then fall into this this separate method of playing against a memory bounded opponent. And this is really the core of the algorithm. The idea here is that that the adversary, their decision policy is going to be conditioned on the history of plays by both other agents, and that induces a Markov decision process in a particular way. And I think it's best illustrated. So let's say that the other agent has a memory size of 2, then they could have a different action for any combination of past actions by itself and the other agent. So this is the state such that we both played S 1 time step ago and we both played B 2 time steps ago. That could lead to some distribution over actions. And so now every action that Alice takes does 2 things. It gives a payoff, and it also gives a transition, right? So after taking an action, if Alice takes the action S, well, we know that this, the history window is going to shift left. So, the 2 action time step ago is going to become SS. And then the next action will be Alice chose S, and then the adversary can take some other action. And so you'll then now be in another state. And so by modeling it in this way, you can sort of allow the agent to lure the other agent into a state such that it takes actions that you can then exploit. And that's sort of you could think of it as bluffing in poker or something like that. But it's sort of a nice formalism. And so the adversary induced MVP would be, if you're in this state where the last 2 joint actions are shown here, then perhaps Bob takes action S with probability 0.3 and action B with probability 0.7, then here's what the transition function would look like. There's 2 possible next states and the reward of 2 or 0 as a result of them. And so the question here is how can you find well, the optimal policy for this Markov decision process is the optimal way of playing against Bob. And so there's 2 things you have to do. One is identify Bob's policy, and then you have to solve what's the optimal policy against that policy. And so one of the steps here, since we didn't assume we know exactly what memory size Bob is using, in my example, it was a 2-step memory, but it could have been a 3-step, a 4-step memory. Each one gets more complicated. There's a step of this algorithm that's trying to estimate that how much history Bob is conditioning his actions on, and then if it turns out that it looks like Bob is not not a memory bounded adversary with a memory size less than the maximum, then you drop to the safety strategy. This is probably the most complicated part of the algorithm. I'm not going to go through it in detail here, but there is a step that's the find k, how big is Bob's memory, that basically boils down to how much extra information, predictive power do you get if you look at all the history of Bob's past actions and model Bob as having a memory size of 2, 3, 4, etc. So, like, are you more, if Bob actually has a memory size of 2 and you model Bob with a memory size of 1, well, then you're not going to be very predictive. But if you model with extra memory, with a memory size of 3, it'll take more data to learn Bob's model, but you'll still be just as predictive. And so there's a way of sort of categorizing or calculating how much predictive power you get by modeling Bob with different memory sizes, and then you identify k from that. And then it's, the algorithm is chosen very carefully to be able to be analyzed. So it's not designed to be a practical algorithm. It's designed to have polynomial time convergence to the optimal policy. And so that, we have a lot of analysis in the paper of what's the how many samples do you need in each of the various stages, and in all the relevant properties, it ends up being polynomial, and it's relying basically on the RMAX algorithm for planning. This is I don't know how many people are familiar with RMAX, but in the same way that Q-learning was one of the first algorithms to be analyzable, that it converges to the optimal policy in the limit eventually. RMAX was one of the first algorithms that you could analyze that it could converge to an optimal policy in polynomial number of mistakes, not polynomial time, but polynomial number of suboptimal actions. And it does this by model-based exploration. And so the sort of core part of playing against these memory-bounded adversaries leverages RMAX very heavily. And then there's some results in the paper that show that compared to some of the alternatives, it's able to exploit other agents optimally, and whereas several competing algorithms from the time were not able to, and in self-play it was able to converge to a Nash equilibrium. And so I know I probably have raised more questions than I have answers, but the main point I want to get across here, for those of you who are motivated by the theoretical side of multi-agent learning, that there is this algorithm out there called Seamless that does have these three, I think, very nice properties for multi-agent learning: convergence, targeted optimality against memory-bounded adversaries, and safety. And the full details are in our I guess in the journal article from 2013, and there's some extensions. All of this appears, or most of this appears, in Doran Chakraborty's PhD thesis, which you can find on my webpage. Yeah, the main journal article is from 2013. So that was the first topic, and if for those of you who are less motivated by the theoretical side now, and that you found that less interesting, and you were sort of drifting off, then now's the time to come back to attention, because I'm going to completely shift gears to some just very brief descriptions of things we've done with regards to traffic congestion and cooperative perception, and then I'll end with our work on Gran Turismo that's quite recent. Like I said, this next kind of piece of work is very heavily motivated by the fantastic work by Eugene and Alex and many people here. The demonstration that you were able to use reinforcement learning to reduce traffic congestion. And in collaboration with Daniel Urieli, who's at General Motors, I think has also interacted a lot with you guys. He's a former PhD student of mine. we looked at trying to extend this to in directions that I know you've also looked at, but into more large scale and open road networks. And we had an AMOS paper where we did rather than in the ring road scenario, look at the sort of the merge setting where there's RL agents sort of sprinkled along but not going in the circle, and also looking at sort of more complex scenarios with more vehicles, and so we're trying to get the flow paradigm to work in open and large networks. And the original paper that we had in AMOS did the main thing that we found for the larger networks was that we could train on the we were using deep reinforcement learning for each of these agents. We experimented with a bunch of different parameters that we report in sort of how the what we needed to do to be able to get the agents to learn well in the shorter open network. And then for the larger network, we were able to use what we called sort of a windowed approach, where we sort of put a window across each of the intersections, and pretended they were each the sort of microcosm, the learned network here, the smaller network. What we've been doing more recently is trying to find a single policy that will work under a whole variety of conditions. Because what we found was that you often needed to, if we trained under similar conditions that we evaluated on, meaning the same road network, the same amount of traffic, all of that, we could outperform, that we'd have better outflow, but than the human baseline. But that it would be very difficult to get it to generalize across different sort of placements of the autonomous vehicles, whether they were evenly placed or randomly placed, different traffic flows, different fractions of AVs in the traffic, different road geometries. And we've now, we have I think it's up on arXiv, we do have a paper that identified sort of a single training regime that learns a policy that will generalize to all of these different conditions, and even shows signs of generalizing also to double lane roads, and the multiple merging settings. And so it's still ongoing work, but we found this this domain to be a lot of fun and inspiring. Although we've probably you'll identify with, we've been quite frustrated with Sumo lately. I guess Eugene, you guys have put out a new simulator, maybe motivated by that. But anyway, this is some work I just wanted to briefly make you aware of. And then similarly, in a similar sort of whirlwind style, a paper that we just had at CVPR a couple weeks ago on end-to-end driving with cooperative perception. We've been looking at trying to fix problems like this one, where a car pulls out behind a truck but doesn't see the car coming, and disaster ensues. That could have been averted if there were cooperative perception. And so the motivation here is that if you have a scenario like this one, there's a vehicle that's violating a red light, there's another car here that can't see it, there could be another one that can communicate to the one that's not able to see, and sort of avert the disaster. It sort of fills in the world model through cooperative perception. And so that's the motivation. We created a series of sort of simulated scenarios in Carla, where there's sort of an overtaking of a parked vehicle, or a blind left turn, or a red light violation, and then ask the question: Can we find? I'm not going to go through them individually. Can we find a way of efficiently, sort of in a bandwidth limited setting, although with a fairly high bandwidth but not infinite bandwidth, train an end-to-end controller that sort of puts the the sensing of the other agents and your own agents into a common representation frame, such that you can learn a policy that is able to take into account not only your own sensing, but the sensations that you get from the other vehicles. And with the assumption here is that you can't just stream full images or full point clouds, but you have to instead compress the representation to something that's actually able to be trained on efficiently, and to be able to be communicated efficiently. And so we learn both the representation and the control policy in a unified end-to-end fashion. And so just like on the right here, you see when there's sharing, you have all of the local sensing that you would have, but you also are able to sort of track the vehicle that's coming across. That's sort of in the scenario when it's important, you're able to fill in a bunch of the extra view. And I think I'm not gonna, again, this is gonna be was going to be just a whirlwind, just to let people know who might be interested in this, about that there is some work now, and this was with Yukeju and Jashun Chui, but the system is called CooperNot, and when it's using this V2V sharing, it's able to sort of complete its perception in an efficient way and learn an effective policy. Okay, and then am I right? I have about 10 minutes left. Is that what we're looking at? Okay, so with the time left, I'm gonna, I have I could again give a complete talk on this. I'm really excited about this work that we've done at Sony AI. I'm going to skim through it so that there's some time for questions, focusing just on the multi-agent learning aspects. But we had a paper with a bunch of different collaborators. First of all, it's a large group project at Sony AI. It's our first really sort of public success that we've had in this very new organization, where our mission is to unleash human imagination and creativity with AI. It was established just a couple of years ago, and we have 4 flagship projects, the gaming being one of them, and this was the one that I've been heading and that we've been working on. Of course, Sony has a big PlayStation business, and so the goal was to try to beat the best world human champions at Gran Turismo, and I'll show you, with some videos what this looks like. But it's a very and we succeeded. We were on the cover of Nature in February. One of the key aspects here is that it's a very real driving simulator. It models slipstream and airflow effects and downforces and friction in a very, very high fidelity way, and it's is such that the top drivers often can go and become train in Gran Turismo and then go and immediately drive at a very high level Formula One race cars. And so we did have events in July and October where we raced against 4 of the best drivers in the world. And as shown here, we actually lost in July, but then in October we were able to beat them after. But a lot of it was improving the multi-agent learning aspects of it. I'm not going to show this trailer; it's online. And again, I'm really going to whip through this. The training was all done through reinforcement learning. We introduced a new algorithm that's a type of distributional reinforcement learning. There's a big compute infrastructure where we were getting lots of different sort of experience rollouts on a bank of PlayStations that were provided by Sony Interactive Entertainment. We also partnered with Polyphony that made the game. And the key challenges to solve here were race control. That's just going really fast on an empty track. That's not multi-agent. That turned out to be the easy part. It took about a day of training to get to human level, world-class human level driving on an empty track. But the tactics where when you have to try to deal with other drivers, and also dealing with the sort of ill-defined etiquette where you can't force cars off the track, and you have to leave them with lines, but you don't want to be too timid either. These multi-agent aspects, it would take another about 8 or 9 days of training to get to world-class levels in the multi-agent problem. And I don't have time to go through everything here. It's like I say, we introduced a distributional RL algorithm called QRSAC. The state features, when it was working on an empty track, it wasn't from pixels. It was from the sort of from a representation that was extracted from the images, but the learning was done in the same kind of API that or interface that the person has. The actions were just throttle and brake and steering angle, and we defined some reward functions. This is when it for the empty track, and used a deep neural network for training, just to show you what it would look like when trained on an empty track. Here's the high speed policy, and again, it's not super smooth. We have a series of blogs now where you can go online and see this policy, but it moves very fast, and is sort of right on the edge of the track, and such that human drivers have now said they've learned some things from what it learned to do on the empty track. It takes different lines than what the person would have. But again, this was in some sense the easy part, just learning on the empty track. The much more difficult part, and again, I'm really flipping through things here, is the opponent aspect. And so when we did start training against other cars, we have a representation where we do get the relative position, velocity, and acceleration of the cars in front and the cars behind. So here, green is the ego agent. It doesn't have a notion of which cars are other copies of itself and which are the human drivers. To it, all the cars are just cars. And all it really gets is this sort of relative position, velocity, and acceleration to the cars. The challenge here was that was balancing between being too aggressive. So here on the is playing a video where it ends. The car ends up being too aggressive and causing collisions, versus a car that ended up being too timid. And so one of the races here, it was, and I don't have the sound on, but the announcer is saying, "Oh, the GT Sophie, that's the name of our car, has a commanding lead. It looks like the person's never going to be able to pass." And then, before the end of this video, the person does end up passing the car. And through sort of, this was in the July race that we ended up losing, we realized that our car actually had hit the brakes. And the reason was, here you sort of see the interface of the human driver, but the car hit the brakes because it was concerned about the collision. And so it ended up giving up its advantage. And so we had this sort of curate the reward function to be able to balance between being too aggressive and too timid, and also following this sort of ill-defined sportsmanship aspect, where there's a human steward who makes a judgment as to whether a collision was one car's fault or the other, and a car gets penalized if it's judged to be their own fault. To learn in this multi-agent scenario, we did have to create a whole bunch of sort of training scenarios where we would start the car. We'd do a lot on the empty track, but then also a 1v1 or 1v2, 1v3 or 1v7 kind of setting where it would have to try to get through all the other cars, and also had it train to do a particular type of passing on a straightaway called slipstream passing, where a car can get behind another car, get in its slipstream, sort of like drafting for bicycles, where there's less air resistance, and therefore even if they're exactly the same car, the one behind can accelerate faster, and then it can sort of slingshot out and pass. And here's what that looks like. Where these two identical cars both are sort of, have their throttle all the way to the ground, but the one behind is able to go a little bit faster because it's in the slipstream of the other car. and then it's able to get an advantage and sort of and pass. And this was learned through experience, but it wouldn't, if we had to make sure we gave it enough examples of this to be able to learn it effectively. And then finally, it mattered who the agent trained against. If it would just train against the built-in AI, it would learn, which is a sort of slow but courteous agent. It would become very aggressive. If it learned against only itself, only in self-play, it became overly cautious. And then in sort of a mixture between these built-in AIs and some self-play and some hand-coded policies that do specific things, it was able to learn a policy that, as you see in this video, is able to drive quite close to a person, not give away an advantage, but also not be too aggressive, and sort of follow a really good line. And my favorite video of showing this actually is I think I'm gonna wrap up by showing you just one last thing, but I think it really emphasizes the multi-agent aspect. There's a series of videos showing you that it does different things depending on what the opponents do. But here's a really nice example of what it learned from a multi-agent perspective. On the track at Lake Maggiore, the red line is what GT Sophie would do on an empty track. And then the green and the gray are actual lines that they took against two of the human drivers, which are in yellow and blue. And what they actually, if you watch this video carefully, at the beginning, the green and the gray are actually out in front. But then they allow themselves to be passed coming in up to the turn by the humans, but in such a way that they have that they keep a good position on the track, and then are able to come out of the turn ahead of the two agents. And this is something that I'm not an expert at this, but human experts at Gran Turismo said this was a very advanced maneuver that they were able to do. Okay, so I'm not, like I say, we have some driver testimonials saying how that they were very impressed about this, that they learned some things from playing with the agent. Again, if I were giving a full 1 hour talk on this, I do have a full 1 hour talk on this on my website if you're interested in the details. But we could go into those. But we're now working on trying to get this out into the actual game, into GT7, so that people can race against GT Sophie. And there's still a lot of interesting challenges, some of them listed here, that remain. But it's been a fantastically fun project where we were able to. When we started this, we had no idea whether it was possible, whether it was going to be possible to outrace the best humans. This is a fundamentally different type of task than say Go or Jeopardy or poker. It's really at the edge of it's a control problem at very high speeds, where if you have to, if you go a little slower, you lose your advantage. A little faster, you can spin out. And it's got a really important multi-agent aspect to it. So with that, I know I went through a lot of material. But if anyone who's, I have some time left. If anybody wants to stick around, welcome to ask some questions. And if not, I completely understand. But thanks for inviting me.
Thanks for coming and speaking. I think somehow Natasha has left the recording on and has left, which I don't know how to turn it off. But what I'll do is we'll cut that out of the recording afterwards. So if you have a question, it will not be posted on YouTube. Yeah. So with that, Peter, just so I know, how much time do you have for questions? When should I cut them off?
I have about 10 minutes. My next meeting is at 15 minutes after the hour. Actually, I left a little time.
Okay, great. Well, thank you again for the talk, and I guess we can open the floor. Does anyone have any questions? Yeah, Rupali.
Hey, Peter, thanks for the really great talk. I have a question about the Sophie AI. Any insights into what you feel made the Sophie AI like better than humans?
Yeah, so I mean, if you go, let's see, where's the, I have a slide on this actually.
Or is it just like a combination of like many aspects?
It is a bunch of different things. But here's one answer to that is we can actually look at where this graph here is showing sort of where the GT Sophie gained ground on humans, color coded by the track here, and so. It was a lot of the sort of you can't if it's just racing on an empty track, it's not going to gain much on the straightaways, right? All the cars are just going to have it straight, throttle straight to the ground. It was at sort of these these are called chicanes, where there's sort of like a little bend in the track, or where there's hairpin turns, things like that. Those make a difference. Those it's able to do a little bit more precisely on an empty track. And we were able to actually to look at the how when the car would accelerate versus brake as a function of the turn. And so this is showing the steering. The orange is GT Sophie, and the blue is Igor Fraga, one of the experts. I don't know why this video can't be loaded, but and then also similarly the throttle and the brake are shown here. And counterintuitively, it actually people thought going in that GT Sophie would learn to keep a high speed longer and sort of brake later going into the turn, and actually instead learned to brake earlier, slow down, and then be able to accelerate faster afterwards. And this was something that surprised the experts. And so, like I said, some of them are now trying to change their tactics a little bit as a result of what GT Sophie has learned to do. And then, so that's the empty track aspect of it. And then, being able to just, pass and, some of the tactics, it was not as good in the first race. The people were able to sort of take advantage of some of its weaknesses. But by the second race in October, it had learned to very well take advantage of sort of where to turn, how to position itself. Like I showed you in that double pass, where it could, sort of give up the advantage at some time so that it would get an advantage later on. And there's actually this video, which I think it'll be on one of our blogs. I don't know why it's not loading here, but it shows Igor Fraga, one of the experts, racing, trying to keep up with a ghost of the GT Sophie. So it's like the ghost, meaning like where GT Sophie had been at the same time. And he's talking about, oh, that was sort of a surprising thing it did there, and sort of gave nice examples of where it was doing better than people. Great question, though.
Thank you.
I guess the next question is Carl's.
Hi, Peter. Thank you for the great talk. And I'm kind of curious about the mechanism that you defined about the aggressiveness and penalties for vehicles touching each other or having collisions. And how did you implement it so that the agents learns to keep a kind of safe distance, but maintain a little bit of like touching and brushing, because that's pretty common in motorsports.
So we actually defined 3 different reward functions, or I guess penalty functions for collisions. One was the any collision. If there's any touching at all, there would be a penalty for it. Another was just a rear end collision. So if the trailing car gets penalized, because then it's clearly their fault. It's almost all, if a car from behind gets into a collision, then that's pretty unambiguously that car's fault because it didn't slow down enough. And then we tried to define sort of through rules what would be called an unsporting collision, which was if there was a side swipe or curve collisions that weren't clearly the opponent's fault. And so we built some rules for what would count as this unsporting collision. And then for those 3 different types of collisions, we actually weighted them differently a little bit depending on the track. So so here you see that the bottom 3 lines here, we raced on 3 different tracks, and for both on the C side, which is sort of the easiest of the tracks, almost all the weight was on this any collision. It just try to avoid collisions, and definitely don't there was always a weight on the on this rear collision. But for SART, we also added this this unsporting collision aspect because there was a penalty there because they're moving at much higher speeds. I think they're like 200 kilometers an hour, and there were a lot more sort of penalties. You needed to make a lot more, be a little more courteous in that kind of a setting. But yeah, when we didn't have that, then they would be a little more aggressive, and there would be bumping, and that was sort of more accepted in these other tracks. And to figure out which one, I don't know where I have it here, but to figure out which policy to use was its own. Where's my slide? It was its own trick, its own question. We'd have a lot of different policies trained. And we had here it is, a big pipeline that did involve in the end human testing of saying, which policy is too aggressive versus not aggressive enough, and is sort of fun to play. We had sort of a human expert who would help us select which one we'd actually put into the race based on how much bumping it was doing and things.
Awesome, thank you so much.
I guess I have one last question before you have to go.
Mm-hmm.
Since it seems like that's the time left. So I'm curious about the self-play aspect of this. I think one thing you mentioned in this is that playing with a bunch of self-play agents looked like the worst thing you could do. And I'm curious for your feelings about what's going on there.
Yeah. Where's my graph that does this, or that shows this? So it wasn't necessarily the worst thing you could do. Yeah, here it is. It's so the self-play was basically the aggressive opponents. It would actually it would end up with fewer collisions. So that you want to be low on the y-axis, and you want to be to the right on the x-axis. And so it was actually learning to be more cautious in self-play, basically, and not really taking the advantage as much. And that was, our basic intuition there is that it's the self-play agents were training. They were sort of aggressive towards each other, and so it was training them to be more deferential in some sense, to avoid the collisions more, and give up the advantage that they could take against one that leaves room for you to go faster. Now this is a little bit anecdotal. I mean, this was we're actually now looking deeper into this and seeing what's a good mix of self-play agents, and how do you do this over over time if you're trying to automate this whole process of training agents. But we did we did find that if we just did self-play, it was basically becoming safe, but not very not quite as fast, as opposed to if it was only against bad agents or timid agents, it would learn to be very fast but not as safe. And we needed to do sort of more of a mixture, and the exact mixture I don't actually recall, but it was some self-play, some built in, and it's described in the Nature article clearly, I think.
Great. Well, thanks again for coming and for kicking off our recorded talks. And yeah, it's been a pleasure hearing from you.
My pleasure. Thanks for the invitation. And yeah, if you have questions, like I say, I know I went through a lot of different things, but if there's questions on, I guess the outline is here. But if there's if there's questions on any of them, starting from the very theoretical result to some of these very brief things I did in the middle to Gran Turismo, feel free, anyone, to reach out.
Then see you all next week.
So long.
Thank you.